All right, welcome everybody to a brand new day. Today we're going to be talking about dynamic programming in. And so if you remember last time, we did a little Fibonacci function. Fibonacci sequence, if you don't remember, goes 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 1, 44, like that. And the Fibonacci function here is going to take in an index. That's index 0, index 1, index 2. And it's going to return the element of the Fibonacci sequence at that point in time. Okay. So if we want to do something like this, for int I equals 0, I is less than 20, plus plus, see out the Fibonacci of I. So let me just give you the Fibonacci. This is the basic recursive Fibonacci function that we do, and then we'll talk about the problems with it. So if x is less than or equal to 1, return 1. Otherwise, return Fibonacci of x minus 1 plus the Fibonacci of x minus 2. And that is a working bit of code, unless I type something in wrong. There we go, 1, 1, 2, 3, 5, 8, 13. Okay. Looks good to me. So what's wrong with this? Well, there's two things wrong with it. The first thing wrong with it is that it's going to overflow. So if I kick this number up to like, I don't know, 40 or something like that, it'll probably overflow by about 40. And no, maybe a little bit more. Let's kick it to like 60. But you might have also seen maybe the other problem, which is you might notice that every subsequent number takes longer and longer and longer to compute. And the reason for this is because, let me hook up my tablet. Not like a computer tablet, an actual drawing tablet. There you go. There's the overflow right there. Okay. The reason for it is because, say 40, page, fibber. All right. So if you call the Fibonacci of 20, this generates a call to the Fibonacci of 19 and the Fibonacci of 18. The Fibonacci of 19 calls Fibonacci of 18 and the Fibonacci of 17. The Fibonacci of 18 calls the Fibonacci of 17 and the Fibonacci of 16. The Fibonacci of 18 calls the Fibonacci of 17 and the Fibonacci of 16. The Fibonacci of 17 calls the Fibonacci of 16 and the Fibonacci of 15. And the Fibonacci of 17 calls the Fibonacci of 16 and the Fibonacci of 15. And the Fibonacci of 16 calls Fibonacci of 15 and the Fibonacci of 14. So if you look at this, you can see that we're going to be repeating work a lot. You can see we have F16 there, F of 16 there, F of 16 there, F of 16 there. And every time you call F of 16, it's going to call F of 15 and F of 14. When we call F of 15, it's going to call F of 14 and F of 13. You are going to be repeating an exponential amount of work. Basically, the rule is for every one additional number in the Fibonacci sequence, you're essentially doubling the amount of work you have to do. And this is highly, massively, and probably inefficient. This is what's called an order 2 to the n algorithm, which is called an exponential or a non-polynomial algorithm. And this is bad. 2 A's. Bad. Okay? Boo. This is really slow. By the time you're trying to compute the 100th Fibonacci number, you're talking about 2 to the 100th power. That's far more than the number of atoms in the universe is the number of operations you need to do to compute just 100 numbers, which you should be able to do like that, right? Because it's just an addition. It's like doing 100 additions. Any modern CPU can just spit that out, no problem. So this is really bad. And so anyone have any ideas of how we could avoid repeating ourselves. Remember the dry principle? I'll repeat it for those of you that don't remember. The dry principle is don't repeat yourself. And here we're repeating that one and repeating that one and repeating that one. We're computing the same function call, which is always going to give you the same result. We're repeating it over and over and over again. By the time you get down to like the Fibonacci of 5, it's probably being called thousands of times. Anyone have any ideas on how we could like not repeat ourselves while preserving the recursive nature of this call? I mean, the obvious thing would just use a for loop, right? And just do it iteratively. An if statement. And if it's been done before, then just use like a saved value, something like that. Is that kind of what you're thinking of, Nolasco? Like, see if we've done it before. Try and save the value. Yeah. Okay. Let's do that. So if you're computing f of 19, then save it to vector.at19. That's a great idea. Let's do that. And you see this thing's still running. Very slow at this point. Okay. So what we can do is we can make a constant size equal to 100. And then rather than just having a 60 sitting there, vector of ints named vec of size. Okay. So you should never have just a raw number sitting in your code like that. You should always use a constant. Magic numbers are bad. You shouldn't have just a 60 sitting in your code. Give it a name, let people know what you're doing, and then you can synchronize them like this. So if I were to change a value or something, then this is both going to change here and here. Okay. So what I can do is I can pass this vector over here, vector of integers named vec to fib, and vectors initialize themselves to 0. That's nice. And I'm also notably not passing it in by const reference because I'm actually going to write to it. Okay, so what I'm going to do is if the value in there is 0, then that means I've never seen this number before. So if I'm asked to compute the f of 19, then I'll check to see if the number is 0. If it is, well, I got to do the computation. If it's not, if there's a value in there already, like 144 or whatever it is, then I will just return the value. So what we can do is say if vector.at_x is not equal to 0. So if we have a value in there already, then we will just return that value, vector.at_x. So if index 0, 1, 2, 3, 4. So if vector.at4 contains a number, it'll contain the number 5, the answer. We'll just return 5. Otherwise, what we will do is say vec.at_x. Otherwise, we'll just return vec.x. So just a little two extra lines of code, and theoretically, well, not theoretically, but we could combine actually these two highlighted lines if we want. This will cause some students' brains to melt, so I don't like writing code like this. But this is actually valid C++. Whenever you do an equals operator, the equals operator returns the value that was assigned. And so we can both assign the value to the vector, and then when that operation finishes, it returns the value that was assigned to it. And so you can actually get a twofer with one line of code like that. I typically break it up into 2 different lines so that students can kind of, have a better mental understanding of what's happening. But this, and what happened here? Yeah, whatever. The two different versions I showed you are equivalent. And so what we're doing is we are going to, anytime we do the computation, we write it down and then return that value. So anytime we do a computation, we can check to see if it has been done before. If it's been done before, we return the saved value. If not, we compute it. So this is learning point number 1, dynamic programming, which means if you ever repeat a computation, like computing the f of 10 or whatever, if you ever repeat it and it's going to give you the same number, then write it down. You know what I mean? So if you're going to be computing repeatedly what f of 10 is, just write it down, and then use the written down value if it's available. You guys understand? Let's see if this works before I get too excited. There we go. See how fast that was? This takes us from order 2 to the n to order n, which is a very, very, very fast speed up. Okay. So this is an incredible speed up. This is exponentially faster. Instead of the heat death of the universe, we're going to solve it instantaneously. Couple different ways we can do this. We're obviously passing in it as a parameter. This is kind of weird though. Like imagine that you're using like CMath or something, and CMath has a Fibonacci function in it, and you want to just be able to pass in 10 and it's going to return to you 144 or whatever. It'd be really weird if that function requires you to like give it a vector alongside of it. Like, I want Fibonacci number 10, and by the way, here's a vector for you to play with. That would be really weird. You know what I mean? Like that. Like that's kind of iffy design. You know what I mean? To require the person calling the function to just provide you like an empty vector, or well, it's not an empty vector. It's a vector filled with zeros. Like that's a really weird function design. So, and it's also a little weird seeing people like pass the vector to every function call like that. It's not a pure function, so it's not even like good from a functional programming perspective. So what we can do is just pull this bad boy out here and make him a global. Okay. Make him a global. Now that size up, got to move up here. We can do this and reference there, and everything's fine. This will actually work exactly the same way. Same output, I imagine. I don't know, I didn't check. Is it? Yeah, okay. -908.1, okay, yeah. Yeah, same output. But now we've got a different problem with our code. You could have a global vector. Very good, Olson. Yeah, you could, but now we've got another problem, which is that we've got a global. And globals are generally considered a code smell. It's really, really, really recommended you not use globals. And there's a variety of reasons for that. First of all, you can't control if anybody else is going to be reading or writing to your vector. Like imagine you've got a million lines of code in this file. And somewhere, down south in the land of cotton, there's a function called foo. And that guy is going to, he forgot to declare a vector. And he just goes vector.at10 is equal to 42. Right, he just forgot to declare a vector. He thought he had, he forgot, and he's like returning a value or something, and it compiles. He's like, oh, that worked, cool. Now your Fibonacci sequence is wrong, right? And if you're gonna ever reuse that value, then oops, like. Everything's like you don't know if some other function is messing with it. When you have a local variable, when you have a non-global variable, you're the only person that can touch that variable. And you know that you're encapsulated and nobody else can read or write to it unless they're doing something really, really, really strange and weird with like pointers and things like that. So globals are not recommended. Like if you can go through your life without writing any global variables, you've probably done pretty well for yourself. So yes, maybe sometimes you have to, I don't know. But in general, I would say 95% of the time, you can probably find a better way of doing it than using a global. That said, at least now we don't have the person calling fib needing to pass in an empty or a zero filled array with it, which is a very weird function design. So there's a better way than this. And the better way of doing it is to put the global inside of the function. But we got, yeah, and see now this is a compiler error. Like, oh shoot, I forgot to make vector vec down here. Oh shoot. We want that compiler error, right? It wasn't supposed to be touching the same thing, right? We got one little problem here. What happens to this vector every time you call fib? Every time you call a function, what happens to the variables in it? Resets. Variables are set back to 0. So if we were to compile and run this code, it'll work. It'll give us the right answer, but we are back into exponential slowdown territory, where every number is a little bit slower than the one before it. That's not good. If only there was some way of making a global variable that was only accessible within this function. There is. It's called static. Okay. So learning point number 2. Static variables are global variables, more or less, that can only, if I can type, only be accessed within the function they're declared in. So this is literally the same as if I put the vector outside of it. So it does not reset every time I call the function. It is a global variable. It's as if I had written this right here, like that. Literally the same thing. But the only person who can access vec now, that global, is fib. Okay. And so it is now a perfectly acceptable function. Okay. You don't have that weird thing of passing a vector in. It's got its own vector. You might have an issue with knowing what size it can be, but there's actually a fairly neat artifact of the way that Fibonacci works is that you actually never need to actually use this when you add to it. You can actually just call pushback, because the way that it's going to figure it out is fib 0 gets computed first due to the way it recurses down, then fib 1, then fib 2, then fib 3. So you can actually just push back the values. And so you can actually start with a vector of size 0 and then just push back into it every time. So that's not even an issue also. So just whenever you need a new value, it'll just add the next one into the vector. And so that's a pretty good Fibonacci function we got here. Again, the only change I would make is having the vector start off at size 0, because usually you don't know how many numbers you're going to compute. Now, so do you guys understand static? It's as if I put it in global space. It's a global yeah, it's a local global. It kind of hurts the brain a little bit, but it's a global variable that nobody else can really touch. Okay. All right. What is global space? Up here, int x. So if you make a variable up in global space like this, it's not part of any function. That's what it means by global. It's not part of any function. Then fib here can set x equal to 42, and main down here can read the value of x. You see that? And now anybody can read to it, anyone can write from it, and that's why it's considered a code smell, because you have no control over the order of operations, and everybody's just reading and writing to it randomly, maybe. So if I run this, you'll see segfault core dumped. What did I change? Oh, this guy here. Maybe? I don't know. Oh, I used X again. Okay. Let's make this Y. How about that? Hardest thing in computer science is coming with a good variable name. There we go. And so at the end of the thing, we get 42 as the. If By touch, you mean it can't be changed outside of the function. Anybody can read to this. Any function can read or write to this global variable here. Only fib can read and write to back here. So it's as if we had put the vector up here in global space, but nobody else can see it. Like if we're down here in main and I try like saying cout vector.at 1 or whatever, it's like, vec, I've never met that man in my life, right? Because even though it's a global, the only person who knows about it is fib. Okay. So Garza, does that make sense? Okay. So yeah, this is bad. Like this is just people reading a variable, writing a variable. How do you track? It's like, as an experienced computer science person, like that's just the kind of thing that just causes like, you know, like if something goes wrong and somebody reads a value and writes it in the wrong order or something, and you have also issues with multi-threading. So if you have multiple CPUs reading and writing to the same vector at the same time, then you're gonna have problems. And this actually doesn't solve that problem. So if you have multiple threads all reading and writing to fib, like or calling fib at the same time, then this is going to cause a race condition that might very well result in a crash. So fib itself should only be single threaded, which means only one CPU should be calling fib at a time, due to the fact that vectors can reallocate. Although in this case, we're not using pushback. Yeah, I still don't feel good about it. Okay. Now, what's the other problem we have with our code? Anyone see any obvious problems? Like we're doing our Fibonacci business here. It's going great. And then bam, we got some negative numbers. What the heck is going on with that? How did we, if you add two positive numbers together, I can prove to you the result is positive, which is one of the reasons why I stopped trusting proofs in math. It's like, look, a positive number plus a positive number is positive. That's just the rules of mathematics. And then I did computer science, and I learned how to prove that my math was correct, and I proved that my program was correct, and then it wouldn't work. And yeah, and this is one of the reasons why you can have something provably correct, and it still gives you a wrong answer. Okay, the number was too big, indeed. So you can see right here, we've got, I think it's 1.8 billion. Yeah, so that's 1.8 billion there. So 1.1 billion plus 1.8 billion is 2.9 billion, but 32-bit integers, 32-bit signed integers only go up to 2.1 billion and change. And so it overflowed, okay? And we got a negative number as the result. So instead of 2.9, we got negative 1.3. Getting that right? Yeah, negative 1.3 billion or something. Okay. So how can we avoid overflow? What can we do? What can we do to make sure that this this doesn't overflow? We're doing like 100 numbers. How can we make sure that we're not going to overflow and the 100 numbers that we're going to print out? What do you guys think? Min-max? I guess we could like we could do something like this, right? We could like assert that x is like less than. What number is it overflowing on? Let's find out. So let's print out I. Let's find out exactly where it's overflowing. You know what I mean? You can do that, sure. Okay, so it's overflowing on 46. Okay. So what we could do is we could do this. We could say assert that x is less than 46. And this is the C++ official die function. Gotta write that in all caps. In order for that to work, you need cassert. Thank you. It's actually the C and C++. Some people hate C/C++, but it's a function in both languages, so I don't want to tell you. It's C and C++ both have an official die function. So if you guys remember in your homework assignments, if bad input's passed in, you return bad input and quit. And the reason why we use that die function is not because it's good from a computer science perspective. I use it because then you're, when you die, take that out of context. When I kill my students, when you die, hi FBI, when you die, I can check that against my output, right? Because the input tester, right? The input tester runs your program, passes in bad input, and then it returns bad input and quits. And then they run it on mine, bad input and quits. It matches, you get the test case passed. Assert is a better version of die, but it has a problem. It has a problem. What makes it better makes it a problem for auto grading. Okay. So what's really cool about assert is that it'll tell you the name of the executable you're in. It'll tell you the name of the file that you're in. It'll tell you the line number that the assertion failed on. That's really cool. So you know, so right now when you call die and you've got like 20 places where your code dies, you don't know which one it is. It's dying somewhere. I don't know. With assert, it tells you on line 17 of main.cc, a assertion was thrown. Okay. Well, what was it? Well, we were promised that x would always be less than 46, and it wasn't. You passed in a number bigger than 46 and up. So it's really nice. It's a nice thing. Absolutely pointless for an auto grader, right? Because your line number is probably not going to be the same as mine. You might have a different format for the assertion. You might say 46 is greater than or equal to x. I don't know. The name of your file might be different. So I can't use assert in the auto grader. I mean, I probably could, but it's just not worth the effort. So we just use die instead. So do you guys understand assert? What's happening here? It's like a spicy if statement, right? So what assert means is it's saying if x is less than 46, cool, do nothing. But if it fails, kill the program. Okay? So if x is less than 46, continue on. If it's not, die. Okay? So we're asserting that x is less than 46. And every time you call the function, it's just going to check, is x less than 46? All right, cool. And if it's not, it dies. It kills the program. But let's say that we want to handle numbers up to 100, right? Right? We want to handle numbers up to 100, up to size. Because this code will not work, by the way. If you passed in 200 here, which I could do, that's one of the reasons why I was segfaulting maybe. If I pass in 200, it's going to try accessing element 200 and kill the program, right? So having an assert that x is within the right boundary is a good idea. I also should probably assert that and x is greater than or equal to 0, right? Because if I pass in a negative number, it's also going to kill my program. What is vector.at -10? Crash. That's the answer. So okay, that's a good approach. We can do an unsigned. That gets rid of this check. We don't need this check anymore. In fact, that's why unsigned integers exist. Unsigned integers are not there so that you don't have to worry about negative numbers. Exactly. They're there as an optimization, so that you don't have to check for numbers being negative anymore. Because if you try passing in -1, it underflows up to max int. And then you can just check it with this, right? So if you pass in -1 now, it would be, some really large number, and the assertion would fail. So we got to make x a unsigned long, and the return value here, let's just do... Let's do this. Using unsigned 64 equals unsigned long. This is something called a type alias. if you don't want to type a long name over and over again, you can do this. Unsigned 64-bit. There we go. What type are we going to return? Unsigned 64-bit. You lose a little bit because this thing isn't highlighted in green anymore. You know, int is green, yeah, or whatever color scheme you guys have. So we do lose that. A vector of U64s. Int. Should still return that. And maybe we can make you a U64 too. I don't know if we care about that. Okay. Cool. Well, that worked, right? At least there's no negative numbers. 2 plus 4 is 7. 1 plus 2 is 3. 3 plus 5 is 8. 13, 22, 36. Looks pretty good. Do you guys, have we solved it? Is that it? Are we done with our overflow problem now? Take a look at the numbers. Tell me what you see. They're cutting off at the end. How about those three numbers right there? Yeah. That's an overflow. That's an overflow, all right. It gets longer than shorter. Yeah, as long as it keeps getting longer, you're like, it's probably working. When the numbers start going down the other way, when you're doing addition, you're like, yeah, we still got an overflow. It's not as easy to see, by the way. When you have signed integers, the negatives just scream at you, overflow error. With these, then you actually have to like sit there and like add them. Like, okay, 1 plus 2 is 3, 4 plus 3 is 7, or you can start from the right side. Seems fine. I don't know. You know, and it gets kind of, you know, annoying to check for because you can't check in your code, right? Because if you check to see if two numbers overflow by adding them, that'll overflow, you know. And you're like, well, what if the number's less? It's really actually annoying to check for overflow. There's the compiler will actually give you some built-in. There's like some built-in GNU functions for G++. We'll actually check for overflow for you. It's really annoying. And you know, just my quick and dirty way is like, oh look, that number is smaller, you know, in digits, so it's an overflow. Okay, and again, we get an overflow here and an overflow here as well. So we didn't quite make it to 100 without overflowing. Okay, well, what's bigger than an unsigned long? Somebody's read hints.cc. Yes, there is it's not part of the standard library. The standard library sort of tragically does not have what's called a big int type in it. A big int type would be an int bigger than 64 bits. It doesn't. So what you have to use is something called the boost library. So in your Zeta directory, and we're going to talk about Zeta later on, there's a very important file there called hints.cc that will help you a lot with your homework. And just copy this over here. I'll just copy the whole thing. Why not? Yep. CD minus puts you back in the directory you were before. Let's see. Useful. Yep. And vim main.cc. And we can do this. Sure, why not? Okay. So learning point number 3. Infinite precision integers with CPP int from boost. So boost is it's like the standard library, but it's not standard. It doesn't come with every installation. It's kind of like, the analogy I like to use is it's like the minor leagues for baseball. And so a lot of things in the standard library right now used to be only found in boost. And then after boost had kind of proven that these things work, then they get adopted into the standard officially. So boost provides a big int called CPP int. And it's like a beta kind of, but I mean, there's a lot of stuff in there that'll probably never make it into the standard. It's not exactly like tryouts or something for the big leagues, but it's a very popular, very standard. I don't want to say standard, but it's almost the standard library. It's very close to the standard library. Like most C++ programmers know it and use it for various parts here and there. It's large. There's a lot to it. The thing that we're going to be using today is the big int, which is called CPP int. And so what we can do with that, actually, if we want to be very clever here, we can. Well, actually, let me show you how CPP int works first. Okay. So CPP int x is equal to 10. CPP int y is equal to 42. Cout x times y, x times y, sorry. Anyone want to guess what number this is going to print to the screen? Notice how easy that was to write also? So instead of an integer, I have a CPP integer. I don't think the name is particularly good. I don't know. Because it's not like a C++ integer. It's a big int. It should be called big int. 420 is correct. So we compile it, run it. Notice there's a lag in the compile time now. We did, in fact, get 420. Okay. So what if we have 42 million billion? So what is 10 times 42 billion? Can I handle it? Will it blend? What is 10 times 42 billion? $420 million. Let's see, count that out. Good. Yeah, 420 million. All right. What if we want to go out a little bit further? We're going to run into trouble because these numbers, by the way, whenever you have a number by itself, it's called a numeric literal. Okay, so 10 is a numeric literal. A literal just means a number just like in your code. The trouble is C++ doesn't have any literal types because remember, this is not part of the standard library. It's not part of the language. There is no literal type that can actually handle 42 exa, whatever, I don't know, penta. I'm just going to call it a hella. So 42 hellas. You can't actually store it this way. And so the CPP int has an alternative way of initializing its value, and it is by using a string. So strings can have infinite length, and so you can actually initialize y to 42 hellas by putting it in double quotes like that. And so it'll convert from a string into the big int type. If we compile it and run it, you'll see we'll get 420. Hello. Interesting. What happened here? Oh, right. Yeah. One annoying thing about it is that it doesn't support the hyphen separators. Which, come on, guys, get with the picture here. That's a valid number in C++. You should update your thing. It's been 12 years. You should support it now. Anyway. So yeah, so you can see we now have 420 hellas. I imagine. I'm not counting those zeros. Okay. You guys got it? So you can make a integer that has any size effectively that you want. The size of the integer is limited by RAM, and I've got 64 gigs of RAM, and that's a lot of digits if you're using 64 gigs. Does it work with spaces? Good question. No, let's find out. Nope. Maybe commas? Let's try with commas. Nope. Kind of annoying. Okay. So, what we can do here, now that you guys understand CPP ints, like that, So basically, anywhere you see an int, you can replace it with a CPP int, with some exceptions. So if we were to replace the size up here with a CPP int, then this vector declaration here is going to complain at us. Because vectors take an integer, technically they take what's called a size, vector.size returns a size type. Size t is unsigned long, basically. So it's basically a 64-bit unsigned integer and it takes as a parameter for its size a 64-bit unsigned, and it returns when you call .size a size t. That's the technical name of the type, an unsigned 64-bit. It's what it is. On the 32-bit system, though, size underscore t would be a 32-bit number. So you cannot rely upon size t being 64 bits. Like there's 32-bit systems out there, and it would shrink on those systems. So CPP int is bigger than a size t, so it does not accept it. Well, yeah, more or less. So what we can do is just convert it to a size t. This is not guaranteed to work. Not guaranteed to work, so we can probably put an assertion in there, you know, assert that the size is like, I don't know, less than or equal to, how many Fibonacci numbers might we need? Like 1 million? I don't know. Sure. So with that, then we've constrained it successfully. Okay. So, or we could just leave size a size t. That's probably, well, it was an int before, but it really should be a size underscore t. That works as well. There's no reason for size to be anything other than a size underscore t, and that is fine. We might get yell. Oh no, it's an unsigned 64. It'll sometimes yell at you if you mix signed and unsigned integers together, and for good reason. But we're good right now. Okay. So we're keeping the vector under size a million. Vector of U64, vector size. Okay. So rather than a vector of U64s, we want to have a vector of CPP ints. Okay. Or if we really want to be we can do that. And just change everything to a CPP int, but I'm not going to do that. Just a U64 should be a U64, if you know what I mean. Okay, so static vector of CPP integers. It's going to return a CPP integer. And that's it. That was it. So we had to change two things. So before we had a vector of integers, and now it's a vector of CPP integers. Before it was a return type of integer. Now we return a CPP integer. That's it. That's all we have to do. We change this. Maybe not. It's fine. Okay. So literally you just replace int with CPP int, and that works for almost everything. For some things like the size of a vector, it won't work because it's too big. But, for almost everything, you just replace int with CPP int. And now, look at it. It's beautiful. We no longer have a maximum size to our numbers. Yeah. So if we want to keep this ball rolling, we could take it up to 300. These numbers get real big. Yeah, see that? You just keep going. They get quite large. What does CPP mean? It means C++. It's not a good name. It's honestly not a good name for the type. I would have called it big int myself. But I didn't write it, so I don't have the ability to name it. It's the author's prerogative. It implies that C++ integers should be better than C integers. That is hilarious. I think probably what it takes its name from is the Boost multi-precision library is built on top of what's called GMP and GMP++. So there's the GNU multi-precision library. And see, they call it Big Num. I don't know why they couldn't. Okay. And so GMP has a C++ version. It's called GMP++. And so the name probably comes from that, because I believe they had a name, something like that. I don't remember off the top of my head. I suspect it probably is because Boost used that to do their implementation. So that's my guess for where CPPN came from. It's still not a good name for a variable. All right. So let's talk about Zeta. So if we go into the Zeta directory, so what you're going to do is this assignment is it's got like 4 levels of analysis that you have to work at. So let's talk about it in a top-down perspective. So what you have to understand is that not even I understand the math theory here. So don't ask me what you'd use this for. All right, so pi of 10, let's say. This number is 4. Pi means count the number of primes up to that number there. And so we've got 2, you got 3, you got 5, you got 7. Thus, there's 4 of these, so the pi of 10 is 4. Okay. You guys understand that? So in order to write this function, okay, let me give you another example. What is the pi of 6? How many prime numbers in Alaska are there from 1 to 6? 1's not a prime number, by the way, so we might as well say from 2 to 6. How many prime numbers are there? 2? Wrong. There is 2, there is 3, and there's 5. So the pi of 6 is 3. This is the prime counting function. Yeah, it's counting how many primes are less than or equal to 6. Okay. Now, what about the pi of 100? How many primes are between 1 and 100? Gotcha. How many primes are between 1 and 100? 25 is correct. Very good. That's in the hints file, by the way, in case you're wondering how he did that so fast. 25 is the number. Okay. So if we wanted to compute this number, we could do like a for loop, right? We could say like for int I equals 1, I is less than or equal to 100, I plus plus, count equals 0. If is prime I, count plus plus, and then you return count. All right. So if you're gonna write pi here, basically it's just a for loop, and you just go from all the numbers from 1 to, in this case, 100, and just say if it's prime, add 1 to our count. If it's not, don't. Now, that's all well and good. It's a good first pass. In fact, I'd probably start your code working this way. You know, just write a pi function that just counts all the primes. Is there a function called isPrime in the standard library? No. So who has to write isPrime? Who has to write a function that takes in an integer and returns true or false if it's prime or not? You do. No, actually. I mean, you probably will as a first pass. You're probably going to write some sort of function. Yeah, very good in Alaska. You're going to return a Boolean. You're going to call it like is prime. Use snake case maybe, or camel case. Either way is fine. Int x. And then how do you tell if a number is prime? Do you guys remember how to do divisibility testing? You could write a divisible by function. You could. And so you would have the pi function calling is prime, calling divisible by, if you want. But how do you check to see if a number is prime? Like let's say they pass in 21 here. How do you tell if 21 is prime or not? Jacob does exactly 2 factors. Or you can just say, well, don't check for 1, don't check for 21. And then just, if any of the numbers in between, from 2 to 20, if any of the numbers in between 1 and 21, if any of them divide in, then it is not prime. So you do something like this. For int I equals 0, I is less than x, I plus plus. If is divisible. So if x not equal to 0, sorry, equal to 2 probably. Don't want to start at 1 either, right? So your eraser not working. Cool, neat. Never changed Microsoft. So if x is divisible by I, then return false. Right, so if 7 divides into 21, which it does, we return false. But if we get through the whole for loop and none of them divide in, then we return true. Okay. So this would be a very basic first pass is prime function. This is kind of ridiculous. You actually don't need to check all the way up to 20, because if you're, by the time you get to checking if 20 is divisible into 21, you would have already found the other factor prior to this. So you actually only have to go up to the square root of x. So if you're searching for divisors of 30, square root of 30 is 5 and change, so we'll go up to 5. And so you can just check to see is 2 divisible, 3, 4, and 5. Because by the time you got to 6, you've already found the other factor of 5, right? So just dropping my tablet. Hopefully it's not broken. So that's a little bit of a optimization you can do. So instead of doing x operations, instead of doing order n, you can do order square root of n. Okay. Definitely a little optimization. Yeah, and then you can write your own is divisible function here. Now there's one other level of analysis, and that's at the very top actually. So what you're actually computing is the summation of all pi of x from x equals, I to j. So what you're going to do is you're going to sum up the pi of, let's say, 100, like if this is 100 and this is 103. So you're going to sum up the pi of 100 and the pi of 101 and the pi of 102 and the pi of 103. Okay, so there's 4 levels that you have to operate at. And this is what Zeta is here to teach you about. There is the summation level, this level. And that level calls a function called pi of x. And then, right, because you're calling pi 1, 2, 3, 4 times here. You can call it thousands of times though. So the summation level is calling the pi level. The pi level is going to call the prime testing level. And the prime testing level is going to call the divisible level. So you have to be able to think about it and raise your consciousness and lower your consciousness between the different levels of analysis. So Now, what I'd recommend is just doing a quick and dirty implementation of all of these things. And then what you're going to find is that your code is too slow. And there's a couple reasons for this. First of all, the prime test here is an order n algorithm, order square root n if you do the optimization. The summation is going to be another order, basically n. So if you go from like 0 to n, then n times you're going to add up. You're going to call pi. You're going to call if you say from 0 to n, you are going to call pi, the function pi, n times. This function here is going to prime test all the numbers from 0 to n as well, because this is the prime counting function, right? So if you pass in the pi of 100, it has to count, hey, is 1 prime? No. Is 2 prime? Yes. Is 3 prime? Yes. Is 4 prime? No. And it's adding them all up. And so n times, you're doing n work, and then for the prime tester, you're doing n work as well. So this works out to be an order n cubed algorithm. Divisible is very easy. It's just a single operation. Okay. So what you're looking at for your basic, like, just get it working implementation is you're looking at order n cubed running time. Because n times you're doing n work, and each one of those times you're doing n work, and this is bad. Okay? So there are a couple tricks we can do here to get this down to about order n total. Because you're never going to do less than that, right? Maybe you could do better, but we're gonna take it from order n cubed, which is going to take a really, really long time, to order n. We're going to do this by reducing the time of the prime test from order n to order 1. We're going to reduce this from order n to order 1 as well. Okay. So do we need to get super efficient or just efficient enough to pass all the test cases? That's all you need to do. Just efficient enough to pass the test cases. Like I said in this class, speed doesn't really matter, but if you do a really poor basic implementation of this, you're probably going to time out and fail test cases. So how can we do this? These are two different optimizations that it's going to drop us from order n cubed to order n time. That's a lot of improvement, right? If n is like 1 trillion, you're going 1 trillion times faster. It's a lot. So we're going to be able to do this using dynamic programming. And we're going to be able to optimize the prime test by using Miller-Robin. Okay. And so the Miller-Robin primality test doesn't need to actually factor the number to tell if it's prime or not, right? If you want to know if 25 is prime, you say, hey, does 2 divide into it? No. Does 3 divide into it? No. Does 4 divide into it? No. Does 5 divide into it? Yes, it's not prime. Miller-Robin does not need to do that. So if you have 1 trillion, your basic prime test thing is going to do 1 trillion operations, or if you're optimizing it, a square root of trillion, which is still a lot. Miller-Robin can get anything done in like a very, very minimal number of steps. Typically, we use like 30 or something like that steps. So it's like order 1, basically. Order 30 is the same as order 1. So the Miller-Robin test is a probabilistic prime testing algorithm, which means if I hand you a number, like a big 50-digit long number, if I hand it to you and you run Miller-Robin on it one time, if it tells you the number is not prime, it is accurate 100% of the time. If I hand you this number and you're like, yeah, it's not prime, that is guaranteed not prime. However, if you run it one time and it's like, yes, it's prime, you have a 75% chance of it being right. Now, I think the actual Miller-Robin function that we use has some additional checks on there. So it's actually more accurate than 75%. But the basic Miller-Robin test is about 75% accurate. And so, and if that sounds like magic to you, take CSI 26 and you'll understand how this kind of stuff works. So if I hand you a number, basically it's like flipping a coin. And if all the coins turn up, it's a prime, 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 then the odds that it is not a prime are very, very, very small. If you've run it 30 times, you have a 1 out of 1 trillion chance. No, it's way better than that. It's a very, very, very small chance that it's not actually a prime. And if that bothers you, then just run it 50 times or 60 times. It's not actually that big a deal. You don't actually need to, for this assignment, you don't actually need to use Miller-Robin that many times. But if you're generating like private keys for RSA encryption or something like that, knock yourself out and do 50 or 60 cycles. You will not see any difference in time on the back end. Your computer can do the test 50 times, in a negligible amount of time, more than 40 times. You won't even see it. So Miller-Robin is going to give you one of your big speedups, and then the other speedup is going to be through using dynamic programming. Okay, so where are we repeating ourselves? Where are we repeating ourselves, and how can we write stuff down? Because that's what dynamic programming is all about. Dynamic programming is write stuff down. If we repeat the calculation. Yeah. So let's say we've computed the pi of 100. And we know that the pi of 100 is 25. In fact, I give that to you. And I'm now going to ask you to compute the pi of 101. Now remember, the pi of 101 means adding up. It means counting all of the pi. It means counting all of the primes from 0 to 101. Right? So how many primes are there from 0 to 101? Anyone know? So this sounds like a for loop, right? You have to start at 0. And is 0 prime? No. Is 1 prime? No. Is 2 prime? Yes. Check. Is 3 prime? Yes. Check. 4 prime? No. Is 5 prime? Yes. Check. 6? No. 7? Yes. And so you'd think that in order to compute this, you would have to do n operations, right? But you don't have to. Not if you know, because this guy has done the same computations, right? You guys remember that? When you count how many primes there are less than 100, you've already figured out if 4 is prime and 5 is prime and 6 is prime and things like that. You don't have to repeat any of those numbers again. You can write it down. Okay. So, in fact, you don't even have to write down if 42 is prime. You don't need to write any of that stuff down. All you actually need to figure out what the pi of 101 is, all you have to realize is that this is going to be equal to the pi of 100 plus if 101 is prime. Make sense? So this number we've written down, hopefully, right? So we've already written down what the pi of 100 is. It's 25. And so to compute the pi of 101, all we have to do is figure out if 101 is prime, which we can do with Miller-Robin. One operation. Done. Is it prime? Yes. Okay, cool. So the answer for the pi of 101 is 25 plus 1. 26. And then when we're going to compute the pi of 102, normally the pi of 102 would be for all numbers from 0 to 102, is it prime? Do it one at a time. Is 4? No. 5? Yes. 6? No. 7? Yes. 8? No. 9? No. 10? No. 11? Yes. Right? But we don't need to. We don't need to repeat that entire computation again, right? We don't have to. Because this value here is not a prime, it's even, right? So we can actually just use the previous number, right? 26. Make sense? So instead of repeating a computation, we can reuse them. Instead of repeating, we reuse. Repeat, reuse, recycle, reduce, something like that. Okay? You guys understand that? This is going to save you a lot of extraneous pain and suffering on this assignment. So the pi of 103, let's see if you guys can figure this out. Let's say that 103 is prime. What is the count of all primes from 0 to 103? Can you guys figure this out? How many primes are there from 0 to 103? 103 is prime, I think. How can you count that so fast? How can you mentally in your head know that 81 is prime and 87 is prime, but 88 is not, and 89? How are you able to do it so fast? Yeah, you just look at the previous number. It's 26. There's 26 primes less than or equal to that one, and then you just say, oh yeah, 103 is prime. So the answer is 27. You do not have to repeat yourself. You do not have to repeat yourself. You do not have to repeat yourself. Okay? That's how I did Zeta. And I gave you guys a number of these starting points also. So if you look at the hints.cc file, these are the number of primes below each power of 10. So the pi of 10 is 4, 2, 3, 5, 7. There's 4 prime numbers less than or equal to 10, right? So this is less than or equal to 1 or 0, whatever, 0. Less than or equal to 100, less than or equal to 1,000, less than or equal to 10,000, so on and so forth. So these are powers of 10. How many primes there are less than a power of 10? And so you can use that as your starting point. So if I give you like a trillion, you don't have to actually count how many primes there are up to a trillion. I've given that for you. That's a good starting point. So if I say, hey, count all the primes at a trillion and 5, then you can jump to a trillion and then go 5 to the right. And there you go. Okay. This is called caching. Caching means writing down a solution so that you don't have to recompute it again another time. Caching is everywhere in computer science. And that should be good. I think that's all you need for Zeta. So yep. At the end of the day, you're just going to sum up all of the results of the pi function. So the summation is going to compute the pi of 100 plus pi of 101 plus pi of 102 plus pi of 103. That is going to have to be order n, unless you're especially clever. You're probably going to have to do n operations there. But this guy can be dropped to order 1. This guy can be dropped to order 1. This guy is always order 1. So that'll take you from an order n cubed algorithm, which is the naive first try algorithm that most students will do. And you can drop it from order n cubed to order 1. And then your code will run lickety split. Okay. There might be a way. Yeah, I don't see any immediately obvious ways of getting rid of this order in here. Okay. Probably no. If it's an answer you already have. Okay. So that is it for today, people. See if there's anything else in Zeta. Yeah, so you've got to compute from like what was that? 100 million to 100 million and 100,000. Add them all up. Hope you know how to do big ints now, because some of these numbers are gonna overflow if you don't have them. Okay. Any questions about Zeta, dynamic programming, overflowing CPP integers, big O running times, how to break down the problem? It's like I said, these are four different levels you're gonna have to operate at here. The documentation for Miller-Robin. Part of the assignment is like I've given you like the name of the function. It's called Miller-Robin. I'm not giving you demo code to do it. So part of the function is finding the documentation. This is how programmers work in real life. You look up the documentation yourself, and you try to find some sample source code, and then you like plagiarize it into. You adapt it into your homework assignment, and get it going, get it working. I see one person typing on chat. So you're going to be Googling how to get Miller-Robin working from the Boost library in your code. Still seeing typing. Well, I'll just stop there.